We've seen now that operator norm continuity at 0, the strongest form of continuity we could hope for, gives rise to a bounded generator for our Markov semigroup. And that means that the semigroup itself is given by exponentiating that generator times t. That level of regularity is rare to see out in the wild if we have a continuous state space, but in the case of a discrete state space, it actually is pretty common. So let's look at that case. If S is a countable discrete state space, then the transition operator is given by matrix multiplication. We have a transition kernel function, Qt, which is just the conditional probability that the process at time t is equal to j, given that at time 0 it's equal to I, and the action of the transition operator on a bounded function is exactly given by matrix multiplication. Now let's note right now that this transition kernel function actually is a bounded matrix in the appropriate form, because remember, all of its entries are in 0, 1, and all of the row sums are equal to 1. That means that the supremum of the absolute value of the row sum is equal to 1 because these are positive. And so that's just equal to the supremum over I of the row sum on the ith row, which is 1. So that tells us that the operator norm of any of these is always equal to 1. In fact, we knew that was true already for transition operators, but it's nice to see it emerge just from the matrix operations. And better yet, in this case where the transition operators are given by matrix multiplication, we have a nice characterization of what it means to be operator norm continuous at 0 or at any time. The operator norm of the difference, Qt minus the identity, as we showed in the last lecture, is the infinity norm, the max row sum norm of the matrix Qt minus the identity. That's given right here. Let's just break up that sum inside into two parts, the term where j equals I and all of the other terms. So that gives us the supremum over I of, well, the j equals I term, we have a 1 here, and Qt of I is less than or equal to 1, so this absolute value is 1 minus Qt of I. And then for all the other terms, j not equal to I, this is 0, and so that's just the sum of Qt of ij. But the sum of Qt of ij over all j not equal to I is again equal to 1 minus Qt of I. And so altogether this gives us the supremum over I of 2 times 1 minus Qt of I. So operator norm continuity at 0 is just the statement that this quantity goes to 0 as t goes down to 0. In other words, since the supremum of a negative is the negative of the infima, the condition is that the infimum of Qt on the diagonal goes to 1. After all, if the matrix Qt is going to go to the identity matrix, then on the diagonal it has to tend to 1. This is a statement that it tends to 1 uniformly over all the entries in the diagonal. The infimal diagonal entry tends to 1. That's what operator norm continuity means here. So all our work from the last lecture shows that in that case, where the infimal diagonal entry tends to 1 as q goes to 0, the transition operators actually have a bounded generator. That bounded generator is given by differentiating Qt of f at t equal to 0 from the right. And that generator A is a bounded operator from which we can recover the semigroup. Qt is e to the ta. But what can we say about that generator? It's a bounded operator on the bounded functions on the state space S, but does that mean it, like Qt, is given by a matrix? Well, if that were true, then what we might expect to be the case is that the matrix is given by differentiating Qt. After all, this is the derivative of this matrix multiplication term and so we would love to pass that derivative through the sum. That would give us the derivative of Qt of ij And that would tell us that A has this as its matrix. That's what we'd like to be true. Now, to be clear, if our state space is finite, this is obvious. This is just the linearity of the derivative operation. And so for finite state spaces, we do have a matrix. Of course, we already knew that every bounded operator in finite dimensions has a matrix, but more importantly, that matrix is given by differentiating the entries of the transition matrix. But if S is countably infinite, then it's going to take some work to prove that this still holds true. So we want to show that the operator A has a matrix, this matrix here, but actually we're first going to have to show independently that it has a matrix. Again, that doesn't follow directly from the setup. Let's explore that counterintuitive phenomenon just a little bit. You might think that every linear operator, or at least every bounded linear operator, should have a matrix. Let's think about how that matrix arises in finite dimensions. We would expand our vector, our function, in a given basis, and apply the operator to the basis vectors to get a new expansion in terms of basis vectors. That gives us the operation of the matrix. Well, let's expand our function f in terms of a basis here. The standard basis we'd like to use is just the indicator functions of all of the points in the state space. Indeed, we can always expand our function as a sum over all states of f at j times the indicator function of the state j. But the problem is, what kind of sum is this? If s is finite, this is no issue. And if f is a simple function, meaning that f at j is 0 for all but finitely many of these j's, then same thing. This is a finite sum and we have no problem. And in that case, we can certainly see that any given linear operator t will act, because of linearity, by taking I to the sum over j of f at j times t applied to the basis vector, indicator of j, at I. And so that suggests that the matrix of t should be exactly given by that. The value of t acting on the indicator function of j, which gives us a new function that we evaluate at I. Now, this is always a matrix for any operator t. The problem is, how can we check that it recovers the original operator? What we would be tempted to do is to try to do an approximation argument. Let's take f, approximate it by simple functions. That gives us this matrix here, and now we will take a limit approximating our f by simple functions to recover the action everywhere. Basic problem here. Simple functions aren't dense in the sup norm. For example, what if f was the constant function 1 on the natural numbers as our state space? Then we could take fk to be the indicator of the first k natural numbers. So certainly fk is converging to f. It's converging to it pointwise as k goes to infinity. But the sup norm of f minus fk is always equal to 1. And in fact, there is no way to uniformly approximate this function by simple functions. It's just not a uniform limit of finite range functions. It's because of that fundamental problem that this counterintuitive fact holds. There are bounded operators on the space of bounded functions which are not given by a matrix at all. So although this matrix here does represent the operator when you restrict it to simple functions, there will be some non-simple bounded measurable functions on which the action of this matrix does not give the value of the operator. In fact, there's no reason why this should even be a bounded matrix in general if T is a bounded operator. So that puts us in a bit of a pickle because we would really like to establish that there is a specific matrix for our bounded generator of our semigroup. Fortunately, what is true even in this context is that matrix operators are closed under limits. That is to say, if I have a sequence Tn of bounded operators on the space of bounded functions, and each of those Tn's is given by a matrix, there's some bounded norm matrix theta n, so that Tn is given by theta n matrix multiplication, And remember that that infinity norm of that matrix is the same thing as the operator norm of Tn. If we also have an operator T is an operator norm limit of the Tn's, then that limit operator T does have a matrix. And that matrix is given by the limits of the matrices of the Tn's. Pointwise. Let's see why that's true. First, leveraging what we did on the last slide, if I take the matrix operator Tn and apply it to the basis vector 1j, then that new function at I is given by summing the matrix entries, theta n ik, against indicator of j at k. Of course, this is just delta jk, and so this sum reduces to only one term. That gives us the matrix entries, theta n of ij, as we would expect. What we can recover from that is that the limit of those theta n ij's pointwise does exist, because it's equal to the limit of this quantity here, and that's going to be the operator t acting on the jth basis vector evaluated at I. Why is that? Because if we take the difference between these two things, well, that's certainly less than or equal to the supremum over all I of that difference. But the supremum over all I is the sup norm of T n acting on this function minus t acting on this function. But that is less than or equal to the operator norm of the difference times the sup norm of that function they're acting on, which is, of course, 1, and by assumption, that goes to 0. So that does show us that this limit exists and is equal to this, as we sought. Now we need to establish the harder property that this matrix actually is the matrix of the limit operator T. To see that, we note that since the sequence Tn is operator norm convergent, it's also operator norm Cauchy. And so if we take the difference Tn minus Tm acting on a function at a point I, which of course is just that difference there, well, those are matrix operators. So that's the sum over j of theta n of ij f at j minus the sum over j of theta m of ij f at j. And these sums both converge by assumption, so we can recombine them into a single sum, the sum over theta n of ij minus theta m of ij times f at j. And what that means, of course, is that the matrix of the difference is the difference of the matrices, as you would expect. And moreover, the max row sum norm of the difference of the two matrices, theta n minus theta m, is equal to the operator norm of the difference of those operators. But since Tn is a operator norm convergence sequence, it's operator norm Cauchy, so that goes to 0 as n and m tend to infinity. But this is the supremum over I of the sum over j, like this. Now our goal is to compare theta n to the limit theta and show that the limit is uniform enough that we actually recover the action of the operator t, from which theta was born in some sense. So to see that, let's note that for each fixed I, if I sum over j theta n of ij minus theta of ij, a quantity which at the moment we don't even know is finite, but we'll see it come out of the wash that it is, well, on the inside, that's equal to the limit of theta n minus theta m, since theta is pointwise the limit of theta m. Since it's a limit, it's also a lim_inf. Now what have we got here? We've got an integral, that's the integral with respect to counting measure, of the lim_inf of a sequence of functions here, depending on this parameter m. We're going to use the least popular, but perhaps most important, limit theorem from integration theory, Fatou's lemma, which tells us that that is less than or equal to the lim_inf of the sum. Now that's true for every I, and for any given I, this sum inside here is less than or equal to the supremum over I of those, which, as we noted above, is the operator norm of the difference of Tn and Tm. So this is less than or equal to the liminf over m of Tn minus Tm operator norm. But that liminf is itself an actual limit because it's just Tn minus T in operator norm. The operator norm is an operator norm continuous function. Now, what we just showed was that that is true for every fixed I, and the quantity on the right doesn't depend on I. So this is an upper bound, and therefore it is bigger than or equal to the least upper bound, which means that the supremum over I of that quantity is also so bounded, but that supremum is exactly equal to the infinity norm of the matrix theta n minus theta. That's less than or equal to the operator norm of Tn minus T. Now, in one fell swoop, this showed us that theta actually is a bounded matrix. By the triangle inequality, this will have finite infinity norm. But it also takes us all the way home to show that theta is the matrix of T, because since theta is a bounded matrix, it defines a bounded operator, which I'll call T hat, by matrix multiplication. And by our result from last time, T hat minus Tn has as its operator norm exactly this quantity here. But we showed that that quantity is less than or equal to the operator norm of T minus Tn, which goes to 0 as n goes to infinity. So that shows that T hat is an operator norm limit of Tn. But the operator norm is a norm, so limits are unique. And therefore it follows that T is equal to T hat. In other words, Tf at I is indeed given by the sum over j of theta ij f at j, which is what we hoped to show. Now, although that was a result about a discrete limit, all limits are defined in terms of limits of sequences if we like, and so this also gives us the result that we wanted. A corollary here is that under the given continuity condition, the operator norm continuity of our Markov transition semigroup at 0, which, as we saw at the beginning of this lecture, amounts to the simple condition that the smallest diagonal entry converges to 1 as t goes down to 0, then the semigroup has a bounded generator, as we already knew, which has a matrix A, and that matrix A is given by the derivative at time 0 of qt of ij. And that's just because, as we showed in the last lecture, A is determined by this fact here. As t goes down to 0, A minus the difference quotient goes to 0. Now, if we take any sequence of times Tn that goes down to 0, that means that A can be recovered as the limit of the qtn minus I over Tn. But this difference quotient here, it has a matrix. And that matrix is 1 over t qt of ij minus delta ij, the matrix of the identity operator. And so, since A is the operator norm limit of a sequence of matrix operators by the proposition we just proved, it follows that A is a matrix operator, and it is given by the limit of the matrices of the terms in the sequence. But that is the definition of the right derivative at time 0 of qt ij. Now from there we can deduce some nice properties of this generator matrix, following exactly the same proof that we gave in lecture 39.2 in the finite case, and that you extended to the converse on your homework. This generator matrix A, given by differentiating the entries of the transition matrix, has non-negative entries off the diagonal and has row sums equal to 0, meaning that the diagonal entries will be negative, equal to the negative of the sum of all the other terms along the row. Now that's going to have some profound implications for us for the Markov chains that have these nice transition kernels as their kernels. And we'll see next time that this gives us a convenient way to understand what these matrix entries are. They are transition rates for the Markov process, and they give us a convenient description of exactly what the Markov process does. The jump hold description of all bounded rate continuous time Markov chains.